All right, so lesson number 21 is on acid-base calculations and polyprotic acids and bases. So we're told we have HS minus, and it has a KB of 1.8 times 10 to the minus 7th. And then we're asked some questions about a solution containing 0.04 molar of this. So we're asked some questions. The first one is, what's the reaction involved? This is important for all problems involving equilibrium, also stoichiometry and all that. So what's the reaction? Well, we have HS minus, and we're told that it's a base. What do bases do? They accept H plus. So if I have HS minus and it gains an H, that'll make it H2S. It was negative, and then it becomes neutral. Where does it gain this from? It gets it from water, right? So I'll have HS minus plus H2O going to form H2S, and seeing that the water lost an H plus, I'm left with OH minus. All right, so that's my reaction, okay? And so what four species are present in equilibrium besides H2O? So first, because this is an equilibrium problem, you can notice the KB isn't huge, right? All three of these are going to be there at equilibrium. Well, we're told one other species is present, and that will be H plus. Why? Because whenever we have water, we get OH minus and H plus. All right, so now that we understand the reaction, now we can start doing the other parts of it. What are the equilibrium concentrations? What's the pH? And what's the percent ionization? All right, so here's that reaction we had. And we're going to do an ice table. So what do we know? We know it's 0.04 molar. We know we have no H2S. We have no H2S, and we have no H2O. Or we don't care about the H2O because it's the liquid. We have no H2S, no OH minus. So now my Q is equal to H2S times OH minus over HS minus. Okay? This is going to give me 0. Why? I have 0 times 0 on top. All right, so Q is 0. K is 1.8 times 10 to the minus 7th. So it's going to shift towards the right. Okay? So that means this will be plus X, minus X. Okay? 0.04 minus X, X, and X. Now I go ahead and I plug this in to my KB. So my KB will be H2S times OH minus over HS minus. Okay, so can I go ahead? Let's go to our next step. In our next step, we're going to go ahead and solve for X. Okay, so this equals 1.8 times 10 to the minus 7th. Okay. This X squared over 0.04 minus X. Can we assume that X is small? Well, notice both Q and K are small, so we can go ahead and we can assume this. So I'm just going to write this up here. I'm going to assume 0.04 minus X equals 0.04. All right, so this then becomes X squared equals 0.04 times 1.8 times 10 to the negative 7th. Let's parentheses clear. This will be a number. Oh, I have it written down here. That's going to be 7.2 times 10 to the minus 9. Okay, so what am I going to do? I'm going to square root this and square root this, and that's going to solve for X. So now my X is 8.5 times 10 to the minus 5. All right, so that's my value for X. All right, or actually, it's 8.49. It's always good to keep some extra sig figs. So now I'm going to go ahead and I'm going to use this up here. So this is 8.49 times 10 to the negative 5 molar H2S. 8.49 times 10 to the minus 5 molar OH minus. This 0.04 minus this number is going to get me 0.0399 molar. This is HS minus. All right. And we need one more species. What's that other species? That other species is going to be H plus, right? So H plus is going to be 1 times 10 to the minus 14 over 8.49 times 10 to the minus 5. This is using the fact that Kw equals H plus times OH minus. And so this is going to get us our H plus concentration, which is, I have this somewhere, 1.18 times 10 to the minus 10 molar H plus. All right, so these are my 4 values. That's my answer to problem number 3. Next, we're asked for our pH. So for our pH, we go ahead and use this value, negative log of it. Before I ever put it in my calculator, I should get a number near 10, right? Something between 9 and 11. And so when I do this, I get 9.93. That's my pH. All right, so that's step number 4. So I have my 4 values. I have my pH. Let's go ahead and do percent ionization. I'm going to go ahead and give myself a little bit of room here. Okay, so what's percent ionization? All right, we're back. We're going to talk about percent ionization. Percent ionization for a base will always be the amount of the base plus that H plus at equilibrium over the amount of base I had at the beginning. So this 0.04. Okay, so it's this number over the initial number. And then I'm going to multiply that by 100%. When I put this in my calculator, 8.49 e to the 5 divided by 0.04, multiply by 100. This gets me 0.21%. All right. So I went ahead, I did all the calculations. Let's look at it on the screen. So the first thing I have to do is an ice table, right? Make sure you remember which direction it is, right? I put that into KB. Here I can make my assumption, right? I made my assumption that X is small, right? I can't always do that, but in this case I can. I find my 4 concentrations. Oops, this is of H plus. And then I go ahead and I find my pH and my percent ionization. We should also remember we can always check our work. We can plug these back into our value for KB to make sure that we get a KB that's close to what we started at. We should also check our assumption. In this case, our assumption is only 0.25% off. All right, let's move on to polyprotic acids. Remember that polyprotic acids are acids that produce more than one H plus. We have diprotic and triprotic. Diprotic produce 2, triprotic produce 3. So we're told that we have H2CO3 and that it is diprotic. And so we're asked for the first and second ionization reactions. So our first reaction is going to be this H2CO3 losing 1 H plus. These are all aqueous. Okay? And now our second one is what's left over losing its second H+. And notice, if I start off at negative and I lose something that's positive, that makes me more negative. Okay? These are my reactions. The second part asks for the Ka expressions. So this is Ka1 will be H plus times HCO3 minus over H2CO3. And then my Ka2, which will be H plus times CO3 2 minus over HCO3 minus. All right, so we have these two ionization reactions. Here they are on the screen. I didn't include the states of these, but they're all aqueous. Okay. This is for a diprotic acid. We can also have diprotic bases, right? Diprotic bases accept two hydrogens, okay? So this was my diprotic acid. Let's do it for CO3 2 minus. We're told is a diprotic base, okay? So it's going to gain an H+. And where does it gain it from? It gains it from water. Why? Because it's aqueous, so it's in water. All right, so it's going to gain that H+. And it's going to leave behind OH minus. Our second one, this now HCO3 minus, it's going to gain its own H+, and that's going to make it H2CO3. Notice, seeing that this is gaining something that's positive, it goes from negative to neutral, okay? And it's going to leave behind an OH minus. These are acids, a diprotic acid. These are bases, a diprotic base, okay? These now, we have KBs, right? So KB1 will be HCO3 minus times OH minus. This is CO3 2 minus. I don't include that H2O. And then I have KB2, which will be this second one, H2CO3 times OH minus over HCO3 minus. All right, and that is it for diprotic acids and bases. Remember, we went through the calculations in the lecture, but you don't need to know those for it. But you do need to know how to write out these ionization reactions and the expressions for Ka. All right, one last thing. Remember that Kb1 is always going to be greater than Kb2, which is going to be greater than, in some cases, Kb3. The same thing goes for our Kas. All right, with that, bye-bye.